How are Ohm's law limitations handled in electrical design? Have you ever wondered how engineers tackle the limitations of Ohm's law in real-world electrical design? Let's break it down together. Ohm's law tells us that the current flowing through a conductor is directly proportional to the voltage and inversely proportional to the resistance. This sounds straightforward, but in practice, things can get a bit tricky. First off, Ohm's law works best with linear materials where resistance stays constant. However, many components like diodes and transistors behave nonlinearly. To manage this, engineers use specific models and tools that account for these nonlinear behaviors. For example, they might use semiconductor equations or simulation software like SPICE to accurately predict how these devices will perform. Next, we have temperature effects. Resistance can change with temperature, which can lead to unexpected results. To handle this, designers often choose components that have known temperature coefficients. They might also include temperature compensation circuits or perform thermal modeling to ensure that resistance changes do not cause issues during operation. Ohm's law is also primarily applicable to steady direct current conditions or low-frequency alternating current signals. When dealing with higher frequencies, components like capacitors and inductors introduce a different kind of behavior known as impedance. This is more complex than simple resistance. Engineers tackle this by using impedance concepts and phasor analysis, employing techniques like alternating current steady-state analysis and frequency response modeling to get accurate results. In more complex circuits, where there are multiple sources and nonlinear loads, Ohm's law alone cannot capture all the interactions. Here, engineers turn to Kirchhoff's laws and network theorems. They often relying on computer-aided simulation tools to help manage these complexities and ensure that the circuit operates as intended. Additionally, there are phenomena like hysteresis in magnetic materials and quantum effects in superconductors that fall outside the scope of Ohm's law. Engineers address these by applying specialized models and principles from materials science in their designs. In summary, while Ohm's law provides a basic understanding of electrical behavior, its limitations are managed through a combination of advanced theories, models, and simulation tools. This approach ensures that electrical designs are reliable, efficient, and perform as expected under various conditions. Understanding these limitations and applying the right methods is key to successful electrical engineering design.